that there are multiple points at which the condensed material is equilibrating. So if it's forming at the photosphere, it's doing its first equilibration at low pressures and acquiring most of its elements just in bulk, except the moderately volatile elements. If it is then falling into the midplane, it is re-equilibrating as it falls, but also even when it's consumed into the larger moon, it's still re-equilibrating through the boundary layer, which is where we've assumed the composition is set. But as you say, you've left behind different elements. You've got radial transport of different elements. And so what we have done is sort of invoked the fact that there is mass transport, but there's also a significant fluid transport to mix vertically, at least. And we assumed that that was sufficient enough also to mix radially as well. And the thing to remember is also that the moderately volatile elements are an incredibly small mass fraction. So even if you enrich the outer portions in moderately volatile elements, it changes your chemistry, but you need to do it a lot to actually change significantly how the different species evolve. So it's definitely an important process, and one that we need to look into. But that would be my sort of the first order argument for why we ignored it in the first case.
But I think, Dave, you are overestimating the role of radial migration of the liquid and the solids, because in the solar nebula that you quoted as an example, the gas is the 99% of the matter. And so you're always in a gas-dominated regime, and that's why you are in the gas track regime. But here, as soon as you start condense, the solids become 90% of the mass. It's 10% in the vapor, 90% in the mass at the buffer temperature, right? Because it's 10% that you are condensed at 90% level. So then you are not in the gas drag regime. It's actually the solids that drag the gas, and not the gas that drags the solids.
So I am going to disagree. So and it comes back to a nuance which I was mentioning. So Dave is right that you have a huge influence from gas drag for two reasons. One is that you are still, as far as the small mass is concerned, you are still vapor dominated, and the extent of pressure support, it can be the pressure gradient can be contributing tens of % of the force balance to your vapor. So unlike the solar nebulous, where it's 1%, you'll have a better idea of that. You've actually got an order of magnitude greater differential velocity between the. So when I'm plotting this, so this is at the surface of the moon. So you're not here in the background gas. You're just dealing with the boundary layer of the moonlet, where you're dominated by the reservoir that's in the large moonlet and not the gas around. So there are other complications we can talk about what is your interacting volume and interacting mass fraction at the surface of the moonlet, which complicate this. But as far as the dynamics in the gas and the small bodies, you're still vapor dominated. This is just the boundary layer.
I don't know the answer, but what I'm puzzling over is, of course, this whole issue of the mass of the moon. As you know, these models always have partly that part of what starts out in the disk, a quarter, a half, or maybe even more, gets back onto the Earth. And in this model, unlike the canonical model, it seems as though that's accomplished in part by a process of fractionation. That's what I'm struggling with. And so it would seem as though the stuff that's actually used to make the moon is volatile rich. That's what I'm struggling with. Because it's the vapor. And the vapor will be more volatile rich than the liquid that forms from it. Now, I could be wrong. It's a complicated system. But I'm just explaining my view.
I think the maybe a helpful comment. So I think this is definitely something that is in my thinking as to how bulk transfer of material as you have condensates and vapor flow. The one thing I would say though is that for a lot of the calculations, it's sort of an all or nothing. You are either something like this, you either have everything in the vapor or you have just moderately volatile into the vapor. And there's a very narrow regime in between. So if your outer regions become are moderately volatile and dominated, there's just basically no gas there. But there's such a small gas mass fraction that by that point you can basically treat it as condensed. Now, that's not necessarily important. You could have, some of that mass condensing onto the moon might still substantiate a significant fraction of its moderate volatile element budget, and that's always an important concern. Right now, I don't have an answer. I'm just saying, yeah, I think you're on a very important point, but I don't have an answer.
But why do you say that the gas is strongly subjugated? Because the synestia needs the completing
So those ones that I was showing you. So this will be a little bit of a spoiler. Here we go. No, actually, this isn't very helpful. So this is now just turning into me showing you my work. Sorry. So let me see if I can rotate this. Yes. So the synesthes I was showing you before were the most compact synesthes that we could form artificially, and they are not typical of the subcapillary nature of post-impact synesthes. So what I'm showing you here are three different cases. So this is the canonical, this is the Schuken-Stewart case, and this is two half-Earth mass merging case. So ignore this one at the end because it's complicated. But what you can see here is that you have a significantly lower angular velocity than comparing to a very long way out from the body. And actually, now I think about it, there's a better plot I can show you where I actually calculate the percentage contribution of each of those things. Each of those forces, and it is on the order of 30-40% of the rotational support is pressure support. So it is a really significant thing. And actually, even within the canonical disk, pressure support, even when it's a relatively low vapor fraction, it's still a significant fraction of the support of the vapor. So yes, the solid is dragging the vapor, but there's a significant differential between where those two reservoirs want to be. If that makes sense. Yes.
I'm probably not following. I'm sorry, but if there's a pressure support in the gas, but the moon is orbiting within this gas, shouldn't there be a drag force on the moon that would cause the moon to spiral in?
There is, so the timescale using the same calculations used for Celneva is much longer, sort of hundreds of years. Now, unfortunately, that's not necessarily the relevant situation for what we're talking about here, because we are dealing with a body that is self-gravitating and is a significant fraction of the scale height. So once it gets a few tenths of a lunar mass, it's pretty safe if it's on a relatively circular orbit. But this is again one of those things that's on my mind of things that make me worried that this whole thing is just going to go drift into the Earth and you're done. But yeah, that's so using the best watch we could. It's stable over the timescale of formation, but there are other complicated dynamics that could mean that it actually moves in faster than a simple calculation would suggest. So TBD. But first order, stable. Second order, I'm going to go and not sleep for a while. I believe that's what's called on a tangent. Great. Cool. Right. So one of the three problems I talked to you about earlier with the canonical model seems to the forming immunosynesthesia seems to offer a very good avenue to solve that problem, because you are forming lunar material and equilibrating it at tens of bars and at temperatures equivalent to the onset of vaporization, and that gives a very good match to the lunar geochemistry. And even outside of the synestia model, this is a very interesting argument for different moon formation models, is that if that is the range of pressures and temperatures you need to be at in order to explain the lunar composition, that actually gives you a constraint on other models as well. Cool. So what about isotopes? So the nice thing about the more energetic impacts that go into producing synestias are that they are themselves more efficient in mixing impact on a target material. They tend to be more head-on. There are often larger mass fractions or higher velocities, and so there is more opportunity in the impact to have intimate mixing between the impactor and the target. But even after the impact, the moon is forming in contact with a large mass fraction of the synestia. So the outer hot regions of the planet are being mixed by the exchange of rain and vapor and convective mixing can be order tens of percent of the mass of the Earth. And because the timescales for that mixing are very quick, on the order of weeks, compared to the timescale of lunar formation, which is years, you would expect the moon to acquire the isotopic composition of tens of percent, the outer tens of percent of the Earth. And so this helps with the explaining the similarity with the isotopes between the Earth and the moon. But it does not solve it. It is not a magical boat. And that is for a single reason, which is that mixing is really hard. Mixing after the impact is very hard. So what I'm showing you here is specific entropy as a function of radius in the midplane of both a canonical and a canonical moon-forming impact and a synestia. And what you can see here is that with radius, the mantle of the Earth is highly thermally stratified. So if you want to exchange material from out here, down here, you have to overcome a huge density barrier to mixing. You also have to overcome a very significant angular momentum barrier to exchanging material radially within the structure. So actually mixing after the impact all of the Earth, or a significant fraction of the Earth, is very difficult. And in fact, actually probably don't want to, because there's evidence from xenon and helium and tungsten isotopes that a fraction of the Earth has remained isolated from the observable mantle from before the giant impact. So there's a fraction of the mantle that wasn't mixed or is inferred to have not mixed during the impact. So we have the sort of, caught between the devil and the deep blue sea, in the sense of you want to mix to explain isotopic similarity, but you don't want to mix to explain isotopic heterogeneity in the present day. But I would like to make the argument that you need efficient mixing during the impact event. That you cannot just rely on post-impact mixing to be the savior of your model. And that, to do that, I'm just going to show you a very simple box model, effectively. And so what I'm going to do is divide the post-impact structure into two reservoirs. One is the one out of which the moon is forming. So in the synestia, this would be the hot outer disk-like regions of the body. For the canonical moon-forming impact, it's the disk and whatever fraction of the planet mixes with the disk. And the second is a lower unmixed reservoir, which does not participate in moon formation, but is later mixed in, or at least substantially mixed in with the rest of the Earth. And each of these two reservoirs during the impact receive different amounts of impactor and target material. So, shown by these guys. So what we can do is say, if I have from the impact a difference in the fraction of impactor that is in the outer region relative to the mixed region. So if these two were identical, if you perfectly mixed in the impactor, you'd be at 0. If you not mixed at all, it would be 1. Versus the fraction of the mass of the Earth which is communicating with the moon as it's forming. So if you're just a disk, you're down here at only like a few percent of an Earth mass. If you're somehow mixing the entire planet up here at 1. And to give you a reference for what present day simulations sort of estimate for these different values, if you assume in a canonical impact that you're just mixing the disk, this is where you would plot. So you have large differences between the impactor and target mass fraction in the two reservoirs, and you're only mixing a very small amount of mass. Whereas what we're showing here is if you take the limiting assumption that you're forming your moon out of the hot outer regions of synestias for high momentum impacts, you tend to mix more, and you tend to mix a larger mass fraction of your body. What these lines are showing is a solution of a very simple set of simultaneous equations, saying that if the difference between the impactor and the target was a given amount in oxygen isotopes, so this would be if it's Mars that's impacting the Earth, and this would be if it's enstatite chondrites, which has been suggested to be that very similar, this is my last one. Similar reservoir for the moon. How much, for a given difference in impactor fraction, how much of the body would you have to mix? Now, ignore the dashed line for a second. It just concentrate on the solid lines. So if I took the published values of the difference between the Earth and Moon from a recent study, I think it's Young et al. 2016, if I said that my difference between my impactor and my target mass fractions in these two reservoirs was 0.2, I'd have to mix, if it's Mars, I'd have to mix all of my planet. You have to mix it all. Even if it's enstatite, I still need to mix 30% of my body. If I'm less efficient at mixing than that, you're basically stuck mixing your entire planet in order to erase the isotopic difference between these two bodies. So what I would argue is, given that you're unlikely to get more than like 50%, and that's very optimistic, 50% of your body mixing after the impact, even if you have a very similar isotopic composition, this is slightly more relaxed for tungsten than it is for oxygen, but even if you have a very similar isotopic composition, you still need to have done a lot of your mixing during the impact. And so I think, as I was saying on Monday, that one of the key things to actually understand the isotopic constraint is still mixing during the impact. That mixing after the impact can erase some of the fine edges, can trim it, but it's not going to be the entire solution to the problem. Now we got sidetracked, so I'm going to just quickly skip to summary, which is that what we proposed is that there are a range of giant impacts, including the originally proposed high momentum moon-forming impacts that can produce a synestia after the impact and then trigger a process of lunar formation. And in that case, the moon forms within a synestia at tens of bars and several thousand Kelvin, which acquires its moderately volatile depleted composition and helps explain some of the similarity in isotopes between the Earth and Moon. Now, afterwards, you need to remove angular momentum from the Earth-Moon system through tidal interactions. But actually, this is the first model to really explain some of the geochemical and dynamical properties of the Earth-Moon system. Thank you. Sorry for going over.
As you mentioned, we took up quite a bit of time for questions. So I'm going to move to the chair's talk and we'll come back maybe to your talk later in the discussion.
So, do you mind? No, I need HDMI. Thank you. Was, okay. Hello? Are we ready? Yeah, you can keep talking, I guess. Where did Mattia go? Mattia disappear?
Yeah, he's escaped.
I should wait for Mattia. I was going to compliment him. So Mattia does all sorts of interesting things, and so the most recent idea is to make a fast-spinning Earth with high obliquity state, initial state, and then have that tidally evolve to the present state. And it's a very interesting scenario. And this talk is about our revisiting of that scenario with what I believe to be a better tidal model. And so there you go. I just said how interesting your work is, Mattia. Where's the pointer? Oh, I should probably. In this new scenario, the Earth is initially rapidly rotating with large obliquity. Tidal evolution somehow reduces the obliquity and the angular momentum, and also the initial large inclination, and it produces a new explanation of the lunar inclination because it works out. So there are three phases in this evolution, and I'm going to talk about each one separately. The first phase is the Laplace plane transition, which has various orbital instabilities, which are very interesting. The Laplace plane transition is when the moon is close to the Earth, the dynamics is dominated by the obliqueness of the Earth. And when the moon is far away from the Earth, it's dominated by perturbations from the sun. And so there's a transition between the two. It's called the Laplace plane transition. And that's a very interesting phenomenon. The next stage is the Cassini transition. This has to do with stability of various equilibrium obliquities of the moon. And this is also interesting. Mattia finds that there's a period near the Cassini transition of a non-synchronous rotation. And then final is, in the last stage, the dynamics is relatively boring, but the inclination damps further due to obliquity tides. And so I'm going to talk about each of these separately. Let's see, the Chuk model is basically similar to other models we've talked about. It uses Wisdom-Hohmann method for the orbits. The Earth rotation is not integrated. It's precessed and the spin is modified by the tides, but it's actually not integrated. The Tuma Wisdom Lee Poisson method is used to model the Earth rotation. And then it includes Earth, Moon, and Sun only. But unlike our model, it includes tides from the Sun on the Earth and cross tides, I believe. But we just included tides from the Earth and the Moon, and so we're going to get a upper limit on how much angular momentum can be withdrawn from the system. They include a formula for intrinsic waddle damping, and then they have an ad hoc model of tides, which I won't go into. And then the first two phases, the Laplace transition and the Cassini transition, are studied with this full numerical model. As far as I understand, the last phase is only studied by using approximate equations. we're revisiting this scenario with this same numerical model that we developed in 2015 to study the first Chuk model. The model already works at high obliquity and eccentricity. It's just a matter of starting with different initial conditions. It was a very general program. I will have to say, remember I mentioned that Zhenliang Tian and I wrote independent versions of the code to check that our codes were correct. But my code was a lot slower than his code. My code was written to be particularly logically clear and had some redundancy in it, and he continued to evolve his version of the code and made it much faster. So it's more than an order of magnitude faster than my code. So all these simulations are using his code. So I'm now dependent on him. I can't do it myself. I don't like that, but it's true. So we include rotation of both the Earth and the Moon. We include the Earth, Moon, and Sun only, but we're only including tides between the Earth and the Moon. And we also add intrinsic wobble damping, but we use a different form. We use the form developed by Peel, which I redrived in a completely different manner in 2016 and got the same rate as Peel in 1973. I just mentioned that wobble damps due to multiple mechanisms. It was shown by Peel around this time that wobble damps due to tides raised on the Moon by the Earth, as well as intrinsic wobble damping within the Moon. And we're going to use the Darwin-Kalla constant Q tides because that seems to be what the Moon does, according to current lunar laser ranging measurements. So the first step is the Laplace plane transition. I mentioned that the basic idea is that near the Earth, the orbit precesses around the normal to the Earth's equator, and far from the Earth, it precesses around the normal to the Earth's orbit. This was done by Laplace in 1805 for circular orbits. There's this very nice paper by Tremaine, Tuma, and Namouni that extended this classical Laplace analysis to eccentric orbits. I hadn't read this paper until I was pointed in this direction by Mathieu, but this is a very nice paper. It focuses primarily on the equilibrium points, but there is some discussion beyond that. So at high obliquities, this is the obliquity of the Earth, the circular Laplace equilibria are unstable in the Laplace transition zone, but new eccentric equilibria develop, and in this range, there are eccentric equilibria for higher obliquities. Some of the eccentric equilibria become unstable, and you get probably chaotic evolution of the orbits. Oh, I already said that. So here's an example from their paper showing a satellite migrating in towards a highly oblique planet. And initially there's zero eccentricity. And then as it evolves inwards, it encounters this first instability. And you get a development of eccentricity of the orbit. And then as you fall further in, you hit the second instability and the orbits begin to evolve chaotically. They don't actually prove that it's chaotic, but it's almost certainly chaotic. But anyway, so now to the Chuk, Hamilton, Locke, Stewart paper of 2016. I should have said. Yes, I did. So here's what they find in their simulations. They find the semi-major axis evolves outwards to the region of the Laplace transition. And then when it gets there, the eccentricity is excited. And then as it's excited, because tides in eccentric orbits damp energy, and that causes an equilibrium in the semi-major axis. And while it sits in this equilibrium, angular momentum is withdrawn. And then at some point you fall out of this situation, and I haven't had time to study why it falls out. But why the seeming axis continues.
The current is pushed under some threshold where it's not being like the transition is not enough. Determined by the obliquity of Earth, but it's complicated because now the moon has like inclination, so it's not 68 anymore. It's something lower that will give you a smooth transition for inclined moon.
Okay. In any case, the initial inclination of the moon is large because it's equatorial and the obliquity is large, but the inclination drops. And in this simulation, it ends up with an inclination between 30 and 40 degrees. And then the obliquity also is high initially, but drops, and it depends upon tidal parameters exactly how far it drops. So in this case, it drops to between 20 and 30 degrees. These are the parameters that they used. Here's our using our model for the same situation, for the same parameters. We find largely similar behavior. The semi-major axis again evolves outwards and has a period where it stalls. The angular momentum drops, and then the eccentricity is excited, and then the inclination also drops, and then the obliquity also drops. But as you can see here, the inclination and the obliquity both drop by a smaller amount than what Matyachuk found. Here's a summary diagram. The summary diagram on the left is the Matya's summary diagram, and the one on the right is what we find. In all these simulations, we chose the same parameters that they did, so they're comparable. And so I guess the main points to look at are that he finds lower final inclinations than we do. He finds lower final obliquities than we do, although there's some overlap. But the main thing is in the abscissa, and that we find too much angular momentum is withdrawn from the system. So he finds a correct Earth-Moon angular momentum at the end, and we find lower than Earth-Moon angular momentum at the end. You could possibly solve these by changing the parameters. So we don't attach great significance to this, but it's we're finding some differences in the results. So the investigated Q of the moon are very low. We find too low of an angular momentum, and we tend to find higher final obliquity and inclination. Remember, the problem is you start with this large inclination of 70 degrees, and you have to reduce it. After these three processes are over, you have to end up with a 5-degree inclination of the moon.
Obliquity is 70 degrees. Inclination is actually 0 degrees. Inclination to a plus plane.
Yeah.
Yeah.
Well, it depends on how the inclination. I'm talking about the inclination to the ecliptic. Yeah. It depends on your reference.
It's always defined to a plus plane.
That's how you define it. I'm defining it with respect to the ecliptic. In any case, so here's the next step has to do with the Cassini transition. It was discovered in 1693, amazingly, just a few years after the telescope was invented, that the moon was in this particular equilibrium state. This is the normal to the orbit of the Earth. This is the normal to the orbit of the moon. This is the spin axis of the moon. And these three vectors all lie on the same plane, and they uniformly regress with an 18.6 year period. So they maintain this configuration as they regress. It turns out that laser ranging has shown that the spin axis of the moon is some fraction of an arc second out of this plane, and that's due to dissipation in the core of the moon. But otherwise, they're coplanar. This was generalized by Colombo and Peale. This is a figure from Peale's paper. In general, there are 4 equilibrium configurations with assuming uniform precession of the orbit. So this is plotting the direction of the angular momentum vector projected on the plane perpendicular to the uniformly. It's in a rotating frame regressing with the node of the orbit, and the pole here is the ecliptic. And so you find that there are Cassini state 1, so Peale numbered them clockwise, number 1, another Cassini's equilibrium number 2, number 3, which is tidally unstable, so it's not ever considered, and 4 is an equilibrium which is linearly unstable. And so you have 2 stable equilibria, and then the moon is thought to have initially formed in Cassini state 1. As you evolve outwards, Cassini state 1 and 4 collide, leaving only Cassini state 2, and then the moon is currently located in Cassini state 2. So here's this evolution as a function of distance from the moon was studied by Ward in 75. This is my reproduction of Ward's results. So beyond about 17 Earth radii, the evolution of the moon is simple, and so that's the situation that Ward studied. So the obliquity of the moon is initially in the systems in Cassini state 1, and then it evolves up to the point where Cassini state 1 and 4 collide, and so it becomes unstable. And then through a period of instability, it falls back onto the Cassini state 2, and then it evolves to the present. However, the assumption that Ward, Peale, Colombo, etc. made that the motion of the moon's orbit is uniform is just not true. The precession of the moon's orbit is not uniform. You already see this in the work of Goldreich in 66 and in our paper, Tuma Wisdom 94. The Goldreich assumed the orbits could be averaged over their orbit periods, making circular rings, but in the final stage, the averaging over the precession timescale had to be done numerically because it was a non-trivial evolution. And so, the lunar orbit is not uniformly rotating. So when you take that into account, you get a more complicated dynamics, which I studied in this paper. This is I don't reference my own paper, 2004, I think. So I studied it as a dynamical system, and Cassini dynamics is a 1 degree of freedom problem, but when you take into account the non-uniform precession of the orbit, it becomes a time-dependent 1 degree of freedom problem, so you can get chaotic behavior and all sorts of resonances. If in that model you choose the orbit to be uniformly precessing, the Cassini problem is solvable, but on the surface of section you find only invariant curves. And then the coordinates here are non-singular coordinates that are suitable for studying the obliquity dynamics. So x is the 2 times the sine of the obliquity of the moon divided by 2 times the cosine of the longitude of the moon, spin axis minus the longitude of the moon's orbit. These are canonical variables, so the Hamiltonian equations are just derivatives with respect to x and y. And then you plot points on this surface of section whenever the lunar node coincides with the Earth's equator. And I've chosen traditional parameters, that the inclination of 5 degrees, and a place in the orbit before the Cassini transition. So in this diagram, you see Cassini state 2 here, Cassini state 1, Cassini state 4, and then as you evolve, these 2 points will collide and this equilibrium will disappear. If you actually include the non-precession of the orbit, you get quite a different behavior. The Cassini dynamics of Peale is not really correct. So you find a lot of chaotic behavior. You see some remnants of the Peale diagram. This is what remains of Cassini state 2. Cassini state 1 now has a funny little secondary island around it, and you find some chaotic behavior. So this is for 5 degrees, and problem, because the inclinations in the Chuk scenario are much larger, this problem that I've just displayed should be redone with larger inclinations, and I expect you'll find a lot of chaotic behavior in the Cassini obliquity dynamics.
In these calculations, the orbit is assumed circular.
No, in these calculations, the orbit is circular, but it doesn't uniformly precess. That's correct. It's not even the case that the orbit is circular, but that's what we assumed in our 94 paper and what Peel assumes. I just mentioned, by the way, that Peel made a big splash with his predictions for Mercury by doing Cassini dynamics for Mercury, and by measuring the ligration and the tilt of the obliquity, you could multiply 3 factors together and get the moment of inertia of Mercury, and therefore decide whether it had a fluid core or not. This was implemented by the MESSENGER mission. But the motion of the orbit of Mercury does not uniformly precess, so the application of the Cassini dynamics does not apply. Okay. I'm trying to get some excited results here. Okay, so here's the Chuk result for evolution through the Cassini dynamics. Cassini transition, there's inclination is initially high after passing through this Laplace transition. As you evolve outwards, this dark line marks where the Cassini obliquity would be if it were stable, but Mattia finds that even before you reach the Cassini transition, you get this is the spin axis. You find a break, you find non-synchronous rotation. The rotation becomes very slow compared to what it would have to be to stay on a synchronous rotation. And then the obliquity, the obliquity pops up and does some funny things. So the inclination, when you develop non-synchronous rotation, the inclination declines more sharply. And remember, the goal is to reduce the inclination to the current value of 5%. So here's our simulation through the Cassini transition. And the red and the blue correspond to different speed ups. So the blue is without speed up and the red is sped up to get to the next stage more quickly. So, so perhaps the most interesting thing is the spin. We don't confirm in our tidal model that there's a period of non-synchronous spin rotation before the Cassini transition, which occurs here. After the Cassini transition, the obliquity behaves in a chaotic way, consistent with the fact that the Cassini state 2 is unstable above a certain obliquity discovered by Boletsky. And so the Cassini dynamics is chaotic, and this chaos is probably well described by the model I described previously. There are some very brief episodes of non-synchronous rotation, but they quickly come back to the synchronous rotation line. So overall, the long period of non-synchronous rotation of the moon is not confirmed by our model. The obliquity of the Earth also increases during this period, and I believe in the Chuk model, the obliquity is assumed to be constant after the Laplace transition. So if you want to match the 23-degree obliquity of the Earth, after the Laplace transition, you have to have even lower obliquity than what Chuk finds. And then we also find some excitation of eccentricity after the Cassini transition. And then the inclination of the moon declines less than it does in the Chuk model. So we're finding a variety of disagreements, but I think the most significant is the lack of non-synchronous rotation. So here's the summary of that part. There's non-synchronous rotation is over a large interval of semi-major axes is not confirmed. The Earth obliquity increases at the end of the calculation, which has to be taken into account in matching the parameters. We find a less significant inclination decrease, which also has to be taken into account in matching the current parameters. But that may be a matter of changing initial conditions. Then the final phase, by including obliquity tides, Mattia is able to reduce the inclination of the moon from where it ends up after the Cassini transition to the current 5 degrees.
inclination. And so you have to go from something like 10 to 15 degrees down to 5 degrees in the latter part of the evolution. Here are the values that Mathieu used. He used the Q of the Earth was 34. The present value of the Earth is 12. And so 34 was chosen so that you could solve the timescale problem. So remember, if you take the current dissipation in the Earth and evolve it backwards in time, the Earth hits the moon 1.5 billion years ago. Well, that's not right. And so the Q of the Earth on average must be larger than what it is today. But the actual evolution of the Q of the Earth is not well understood. There's evidence in corals and sedimentary rocks, periodicities in sedimentary rocks, that the Q of the Earth was similar to this 12 for the last 600 million years or so, and less than 20 for the last billion years. And so it was not appropriate to choose QE 34 during this later phase of the evolution. It should probably have been smaller. But again, it's really not known. So we chose, we ran our model for this just to see if obliquity tides did indeed damp the inclination, and it does. And so we chose, we started at 40 Earth radii at 10 degree inclination, and then with the current parameters of the moon, and we found that it decreased from 10 to 7.5 or 8, 7.5 degrees. It didn't decline to 5 degrees. That's because our Q of the Earth is smaller than what Mathieu used. And so indeed, the amount of decrease of inclination from this period to that period is the delta I is directly proportional to QE. So if you choose Mathieu's value, you would get an appropriate decline of inclination. And if you choose the current value of QE, you don't get enough QE. You don't get enough decline of inclination. But what we basically confirm is that the moon does indeed damp inclination due to tides in obliquity tides. That's maybe the important conclusion. We still have to determine what the history of QE and QM were. Yes?
You still have to constrain the timescale problem. And before 40 Earth radii, a very small part of lunar history is before 40.
In terms of time.
Yes.
In terms of time, yes.
So you have to, this will give you a moon that's younger than 2 million years. Just if they can pass face values.
Well, if the tidal rhythmites say for 1 billion years the Q was less than 20, then back to 40 Earth radii, you probably can't explain a high inclination at 40 Earth radii if you choose the Q to be much lower than the Q that you used. It will increase somewhat, but it won't be as high as you're getting.
Actually, I think it goes the other way, because if you are using a small Q for more recent times, that means for the early time of evolution, which includes times around 40, where the obliquity was highest, you have to then use a larger Q to balance it. So,
yes, you're absolutely correct. I'm only talking about the last billion years. And if you make a Q of 12 during the last billion years, you indeed have to make it be 30 or 40 earlier in order to make the whole evolution span to 60 Earth radii in 4.5 billion years. So it's key to know how the Q of the Earth and the moon vary with time. The point of this is that the inclination of the moon is damped. And it depends upon the parameters. That depends upon the parameters. So we have to stick all these things together, and it's actually not clear at the moment whether you can satisfy all the constraints, because we find higher obliquities and inclinations after the Laplace transition. We find Too much angular momentum is withdrawn. Anyway, and then we have trouble putting it all together right now. And I think that's just a matter of further exploration of parameters. But I would say maybe the most significant result is that we don't find non-synchronous rotation. And I think I haven't traced it down of why, but I think that's again because of another ad hoc factor you put in the tides that make the vibrational damping be less strong. I don't think we have any measurement of vibrational damping to compare our tidal model to. And so, so it depends upon theory. But, okay, so am I done? So the main thing is we have to evaluate how values have changed with time. For instance, the Zonley would like a very high 1,000 or higher Q of the Earth early on. But if it has high Q in the beginning and has very low Q now, and we have to stretch it out so that over 4.5 billion years that you get 60 Earth radii evolution. And then if the Q of the moon was small during this phase, this last billion-year phase, then maybe the magma ocean, early dissipation in the lunar magma ocean did play a role, and that's by Chen and Nimmo. So you would have to fold this in, but that's going to complicate the Cassini transition. And so, so the whole dynamic is going to be much more complicated if you make the, include the obliquity tides during the Cassini transition. I think that's all I had to say.
Thank you.
So this was started about after Jihad invited me. I thought I had to do something for this conference. So this is all done in the last couple months, and we have more simulations running in order to try to pin down the actual parameters that could reproduce the moon. But that's work in progress.
Very nice. So next time for one or two questions at the most, then we'll take a few minutes break before our concluding discussion.
I have some very technical stuff that can you best ask.
Express it through the mic. Yes.
Okay, so I feel much less lonely on this planet now that other people are doing this. So can you show your plot of Cassini state transition?
Excellent. Which one?
Cassini state transition.
Oh, Cassini state transition.
Because lots of interesting stuff going on there. So you say you don't see non-synchronous rotation, but to me it looks like those chaotic regions are exactly that.
No, this is chaotic. This is chaotic obliquity, not non-synchronous rotation.
But isn't M spin also goes up and down like?
There's some brief episodes of non-synchronous rotation, but they quickly go back and follow the basic trend is to follow the synchronous line.
Okay, and so when the moon is librating, you have basically a bulge jumping by epsilon or minus epsilon from one side to the other, or
We're
in terms of angle.
yes, we're using constant Q tides. And I disagree with your remark in your paper that implies that the eccentricity damping doesn't depend upon eccentricity. This was already, the dEdt is proportional to E rather than a constant for constant Q tides was already shown by Goldreich and Kalle in the 60s.
Not the way I implemented it. So I'm skeptical of the growth of eccentricity.
This one.
Yeah, but yeah, that's makes life more interesting. So let's see.
It's interesting, and I can't say I understand it. It's just, at this point, it's something that comes out of the simulations.
Thank you.
Okay. Any other questions?
I leave my question till later, do it privately. So we close this morning's session, and with it essentially the proceedings of the workshop. I want to thank everyone for their wonderful lectures, new results presented, discussion. This was wonderful. We'll take a 10-minute break, and then we move to our concluding discussion. Thank you all very much.
So, coffee is outside, should we need it?